Hello.
Hi, Kinoshita-san. Good to see you.
Good to see you.
Thank you for coming, Kinoshita-san, today.
Thank you.
So, optical quantum computing seems to be relevant now. So, I'd like to ask you to share our vision of the optical quantum computing.
Yes, in recent years, generative AI has advanced and spread very quickly. And as a result, power consumption at the GPU data centers has been rising sharply. At NTT laboratories, we are tackling this challenge in two ways. One approach is IOWN, our next generation information and communications infrastructure, which can make AI data centers more efficient by reducing power consumption and increasing transmission capacity. Another approach is NTT's lightweight large language model Tsuzumi, which makes AI itself more efficient by delivering strong performance with much lower computational requirements. However, these improvements are still within classical computing. If we look ahead to artificial general intelligence or even artificial superintelligence, the amount of computing power required could far exceed what today's system can handle. That's why expectations for quantum computers are growing rapidly. Quantum computers were once expected to become practical in the 2040s or 2050s, but with global investment and competition accelerating, they may arrive as early as 2030s. NTT Laboratories has spent decades researching quantum technologies, and last year we moved into full-scale practical development based on this global trend. Quantum technology is no longer a distant future dream. It's becoming a strategic area we need to prepare for now.
So, there are many ways of the quantum computing. So, why should we go with optical quantum computing?
So there are several approaches for quantum computing, including superconducting and neural atoms and ion trap and optical method. So among them, NTT are focusing on the optical computers because it scales more easily and offers strong advantages for practical business use. One big advantage is that optical system can operate at room temperatures and normal pressure. Unlike superconducting system, they don't require extreme cooling or vacuum equipment, which makes the infrastructure more scalable. Another important advantage is that we can apply many existing optical communication technologies to optical quantum computers, including low-loss fiber, optical amplification, wavelength conversion, and wavelength division multiplexing. On top of that, NTT has world-class R&D capabilities in optical communications, including quantum light source. For these reasons, we see optical computing as the most promising approach, and we are focusing our R&D effort on it.
How do you envision the future roadmap and the future of ICT?
NTT is speeding up R&D on both the hardware and the software for optical computers, aiming for 10,000 qubit in 2027 and a world-class 1 million qubit system by 2030. However, quantum computers can't solve everything on their own. Conventional GPU-based high-performance computing systems are still essential for large-scale data processing and fast simulations. So the big challenge is how to integrate quantum computers and high-performance computers into one unified hybrid environment. At the center of this evolution is IOWN. With IOWN 1.0 to 4.0, we apply optical technologies to data transmission layer across all high-performance computing environment. From IOWN 5.0 onward, we extend optical technologies into the computing layer, enhancing classical computers with optical transistors. And then ultimately enabling optical quantum computers with far greater performance and efficiency. In short, IOWN is the foundation supporting the evolution of both high-performance computing and quantum computing. And it will play a key role in shaping the future of ICT.